Yep.
Yes.
Okay, so it's my pleasure to welcome everyone at this next iteration of the One World I Am Mathematical Physics seminar. Today is my great pleasure to have Bernard Helffer, who's going to talk about semi-classical methods and tunneling effects, old and new. So please go ahead.
Okay, so thank you for the invitation. And so I was asked to speak about tunneling, and so I will try to present a few examples where tunneling was present. So the story starts more or less in the 80s, so 40 years ago. I hope I remember everything because sometimes it was done a long time ago. So I lose the, sorry, I don't have the possibility. Oh, yes. See. So, in the spirit of my talk, we can say that the story started at the beginning of the 80s. And so I will not reproduce the abstract that I send you, but I will just mention now 6 typical problems where tunneling is concerned. And so the first one was the double well problem in dimension larger than 2, because in dimension 1 there was a lot of literature before. The second point was all the analysis of the Witten complexes and the small eigenvalues of Witten Laplacian in relation with the instantaneous method proposed by Witten. The third one was about the imaginary part of the resonance, the so-called problem of the well in the island. The fourth one was in solid-state physics, and the most interesting example was about the proof of the counter structure of the Harper model for some family of fluxes. The fifth one is, in some sense, coming back to the second one, concerns very precise estimates, the so-called Ehring-Kramers formula. And finally, the most recent contribution concerns the estimate of the boundary tunneling for the Neumann magnetic Schrödinger operator, so in relation with problems in surface superconductivity. So I just mentioned dates corresponding to the beginning of the story in each case, but there is of course, there is a huge literature after that, and so it's difficult to. I will surely forget many contributors. I'm sorry for that. Okay, so in the first part of my talk, I will speak about the double well problem. Then I hope to survey very rapidly the 5 other problems, the 4 other problems that I was mentioning, and hope to have some time to present a little more in detail the last topic. Okay, so for the double well problem, so in 1D you can find at least formally the solution, which is present as an exercise in Landau-Lifshitz book. And so, except in the radial case, the question was to have the same kind of estimate in any dimension. And so there are 2 questions around this double well problem. So estimate where to have a rough estimate for the ground state energy, and then more interesting to have an estimate of the difference between the second one and the first one, which should be exponentially small. So to my knowledge, the first rigorous results which are valid in dimension two or more are due to Barry-Simon and at about the same time Helffer-Sjöstrand. So there is also Maslow who claims he has the result, but I don't think his proof was so complete as the proof we have. Okay, so what was the strategy? So the strategy of Barry-Simon was a little different, but so I explained the strategy in my paper with Johannes Sjöstrand. The first point was to prove Agmon estimate. I will come back on this. The second point was to have a rough localization of the eigenvalues through harmonic approximation. So this point was a rather old result. The third point was to construct WKB approximation for one well eigenfunction. The fourth point was to compare the real eigenfunction with the WKB construction. The fifth point was to construct this one well comparison problem. So if you want to treat a double well problem, you have to create start from two one well problem and to put together the information. And then the last point was to implement in some exact formula at the beginning all these attempted all these comparisons to get the splitting formula that is an exponentially which should be exponentially small. So the first point was the Agmon estimate. So Agmon estimates were initially developed in order to measure the decay of eigenfunctions at infinity. But as we will see just now, the basic proof is independent of any parameters, and then this is in the way you use it that you can be semi-classical or considering at infinity. So in my context here, I try to control the L2 norm in some compact set in the limit of a semi-classical parameter h tending to 0. So the basis of the proof is very simple. If you start from some Schrödinger operator, minus h squared Laplacian plus v, then you have this identity. This is energy identity. So I write it in the, we can write it in an open bounded set in Rm or on a manifold or in Rm with suitable assumption. It's just an identity for any Lipschitzian phi. So if you are in open set omega, you have the Dirichlet condition to fix the. So this is an identity. And then what can you do with this identity? So if you implement an eigenfunction UH of this Schrödinger operator, PHV, as associated with an eigenvalue lambda h, you get that exactly this. Let's see, I have to delete that. You get this equality. And then if you forget for sometimes this term, you get this inequality. And so if you know that lambda h is less than E, then you can write it in this way. And this is true at the moment for any phi. So the question is to determine if there is a clever choice for phi. And so, sorry, yes, I have a problem, yes. And so the clever choice for phi is related to the so-called Agmon distance or Agmon-Littner distance. And this consists to replace the usual metric dx2 in R2, say, or in open set of in Rn or in open set of Rn by degenerate metric consisting in multiplying the standard metric by V minus E. And so, so this is a degenerate metric in the sense that in the so-called classical region, you put 0. And so in any connected component of this set, V of x less than E, the distance between 2 points is 0. And so this is an object which is interesting, in the so-called forbidden region, when V of x is larger than E. And then with this Agmon distance, you can do more or less all what you do in the case where you have a metric on a Riemannian manifold. You can define distance and length of a curve and so on. And so now we can apply this for the decay of eigenfunctions. So what you will get from the inequality I wrote before, that exponential phi over h u h is well controlled in a region of this type, omega 1 epsilon 1 h, by exponential, the sup over the complementary of this region. And so the choice of a suitable phi, which could depend on h, is related to the Agmon distance, the Agmon metric, and more precisely to the Agmon distance to the so-called classical region. And so more concretely, you take phi of x equal, so you accept to lose epsilon as small as possible, and you take 1 minus epsilon d of x, where d of x is the Agmon distance to the classical region. And in this way, you have an estimate of this type, exponential 1 minus epsilon d of x over h u h equal mod O of exponential epsilon over h for any epsilon. So this is something where you see we are very few assumptions. This is an a priori estimate for an eigenfunction. Now, so here I write a more precise statement, and but essentially this is what I wrote before. So at the beginning, we only get an H1 estimate in this way, the formula 10. But if you want to come back to pointwise estimate, it's relatively easy using the equation to come back to pointwise estimate. But for most of the work, we actually do not need pointwise estimate, but we need this H1 control of UH and of exponential d over HUH and the gradient of the same expression. Okay. Now, so this was the first point. Control a priori the decay of the eigenfunction. The second point is more standard. It's the harmonic approximation. And this means that let us concentrate in the case where we want to look at the ground state. So near the one minimum of the potential V of x, we replace V of x by its quadratic approximation. And then we get an operator of this type up to some additive constant. And the spectrum of this operator, so it's an harmonic oscillator, is perfectly known. And so in this way, we get an upper bound for the first eigenvalue or any finite number of eigenvalues by modulo an error of size O of h 3/2. the lower bound. So there are various ways to do it. One is to use a partition of unity depending by which depends on H, and we distinguish between the region where V is larger than something, and when V is in the neighborhood of a minimum, we use the harmonic approximation. So this is, for example, pedagogically explained in the book of Sikon, Freus, Simon. So in this way, we have some error like O of H6/5, which is not optimal, but it is enough to start the machinery. Okay. Then once the harmonic approximation is done, so it's possible, this we'll come back to this a little later, it's in some given interval, E of H, between infimum of V and infimum of V plus CH, it is possible to construct a basis of the eigenspace corresponding to this interval, for which the elements of this basis are localized in one of the well. So this suggests that we have to effectively to define one well problem to arrive to this. And at the end, if we compute the matrix of the operator reduced to this spectral interval, E of H, in this basis, we have a so-called interaction matrix, and the goal is to find a way to compute this interaction matrix. And so in the case of the double well, so I normalize assuming that the infimum is at 0. So to simplify, I assume that V naught tends to infinity at infinity, and I take some symmetry, typically the symmetry with respect to hyperplane xd equals 0. And we have two wells, UL and UR, which are exchanged by this symmetry. And then the harmonic approximation says that there are the two first eigenvalues are closed, and the goal is to measure the splitting between these two eigenvalues. So I choose an interval E of H such that there are only these two eigenvalues in the interval. Okay, so this is what I just explained. So in this case, the interaction matrix is a 2x2 matrix, and now I want to compute in a suitable basis the terms appearing in the interaction matrix. And so this suitable basis is constructed with two elements, UL and UR, UL being strongly localized in the sense of the Agmon distance in UL, and UR is simply defined by symmetry. And so the decay of each of these eigenvalue, each of these elements of the basis, UL decay like the Agmon distance of X to UL. So except in UL, the UL is exponentially small. In particular, when UL is close to, when X is close to UR, then you have here exponential minus the distance of UR to UL. So in this construction, the second point is that this UL is well approximated by a WKB approximation. This is not an approximation which is true everywhere, but this approximation is correct in the neighborhood of the set consisting of the point, the geodesic, consisting of the geodesics between UL and UR. Actually, when we are in this kind of region, avoiding UR, this function dvx to UL is a C-infinity function and satisfies an iconal equation. So the main phase in the WKB solution is actually in this region this time. Okay, and so the 2 by 2 matrix, because of the symmetry, so it's self-adjoint. The two, so B, we have B here and B here, so this is symmetric. All the terms are real here, and on the diagonal you have 2 terms. So the goal is not to have a good information on A. So for A, the harmonic approximation is enough for us, but to have a precise estimate on B. And by precise, I mean that we have some expression of this type. B of H is H minus some power, which could be precise. Beta of H is some terms which has a complete expansion in powers of H. And you have the exponentialist term S being the Agmon distance between UL and UR. And in this special basis, it's immediate to see that in this basis, the the eigenvectors are 1 over square root of 2, 1, 1, 1 over square root 1 minus 1. And we get in addition some information that for this choice of eigenvectors, so 1 over square root u1 plus u2 is strongly localized near UL, and 1 over square root of 2, u1 minus 2 is strongly localized in UL. Okay, so now how to compute B? And the computation of B is based on some formula, which is essentially based on Stokes' lemma or Green-Stokes formula, and you get that B has the following form: B equal H squared plus some integral over gamma. Gamma is a piece of hypersurface which is transversal to the set geodesic. So let us assume, to simplify, that there is only one geodesic, and gamma is transversal to this geodesic. So you get this modulo some errors which come from all the Agmon estimates which have been established. And so if you want the main term, you have to look to this term. And then again, now you can replace UL modulo some error by the WKB approximation, and you get this explicit formula modulo this time O of H infinity exponential the distance of U right to U left. Then you recognize here a Laplace integral. And at least if you add some assumptions about this expression, which should you can assume that it vanishes exactly at order 2 at the intersection of gamma with the minimal geodesics, you get a complete expansion. Okay, so this was the presentation of the double well problem. So I recall the main steps: decay estimate, rough localization, comparison with a one well problem, computation of the interaction metric, construction of WKB for the one well problem, control the error in weighted space of the difference between the WKB solution and the one well eigenfunction. So technically, it's rather long to write down all the details, but so this was the strategy. And in many of the examples that I will describe very rapidly now, we follow more or less the same strategy. Okay, for resonances, I will be very short. So here is the touristical presentation of the phenomenon. So you have some island, and here you have what will be a well, and you want to prove in this case that it appears so-called resonances, and which are that means in a suitable sense complex eigenvalues, and which are extremely close to real eigenvalues, and the goal is to measure the imaginary part. So more mathematically, so I will limit my description to a 1D model, and in the 1D case, there were already contributions previously to the analysis I have done with Johannes-Sjöstrand, in particular by Evans Harrell and Barry Simon. But so the point, the novelty in the I don't remember, 84, I think, or 85, the novelty was that we can also treat two-dimensional models or more. So the model is of the potential is this one. So if you look to this and forget the other part, you have a complete semi-classical analysis of this problem. And then you want to measure the imaginary part of the resonance, which is related to the Agmon distance between the minimum and here the first point where you leave you leave the island. And so this is the kind of result that you can get. So in this case, the Agmon distance, so in 1D, it's very explicit. And you get, again, an expression of this type where you measure the imaginary part of this. Here you have 2 times the distance, the Agmon distance between 0 and x1. So you have to think that you are, this is the length of going to the C and come back, in some sense. You start from the minimum, you take the minimal path to see the C, and you come back. So this is the touristical distance, if you want. Okay. So here I just mentioned one point in the proof is, again, you have an exact formula here where W is a suitable neighborhood of V larger than minus epsilon, and the goal is to first eliminate contribution using Agmon estimate, which are far from the point where the distance between the bottom of the local minimum and the C is minimal, and then to have a WKB construction for this so-called resonance state. And here you have to go through points where you have to use Airy type WKB construction. So you have to, okay. Okay, so yes, I choose one of this example because at the moment, using the techniques we have initiated at the time with special definition of resonance, the subject is very active. And so just to mention recent works in the last 5 years, I mentioned many contributions about the so-called Ruel-Polycott resonances. So there are various approaches for this, but these names use clearly the kind of semi-classical techniques that we have mentioned. So also for this problem of the resonance, for the case of the well in Ireland. There are recent contributions by Sjöstrand and Zerzeri, and there are a very recent asterisk by Jean-François Bonny, Tetsuo Fugier, Thierry Ramon, and Maher Zerzeri about resonances for homoclinic trap sets. So, and probably I forget many other people. So the third example is related to the analysis of the Harper's model. So there are various names for this model. Harper, Hofstadter, almost Mathieu. So I've never understood what was the correct terminology. But in the beginning, you can start with this model in small L2 of Z and to look at this operator and to ask for the spectrum. Here you have one important parameter, alpha, which corresponds to the flux, and theta, which is a second parameter, which is unimportant in the case where alpha is irrational, because the spectrum will be independent of theta. But if you want to analyze simultaneously in the case when alpha is rational and the case when alpha is irrational, you have to use to the union over theta of the spectrum that you get for this. Okay, so there was a so-called 10 Martini conjecture that the spectrum of the Helmholtz-Mathieu operator, H lambda alpha, is a Cantor set. So I don't mention theta for the reason I just say, for any irrational alpha. And so I think the terminology comes from Barry Simon in reference to some offer by Mark Katz to give 10 Martini to the author which will find, which will prove this 10 Martini conjecture. Okay, so the question was not solved very rapidly, so there are partial results. I mentioned a few names. We enter in the play with Sjöstrand in '89, but just for a special family of alpha, and then you have Puch, Avila, Krikorian, and finally the final proof if any irrational alpha was obtained by Avila Zhitomirskaya for this model. So, you know, I just take this picture about the Hofstadter butterfly, which corresponds to the description of the spectrum in function of some value alpha. And then on the horizontal line, you have the corresponding spectrum. So here it's typically a picture that you get by looking at spatial value of rational alpha. And so there are many semi-classical aspects in this picture. And this was one of the interests of our approach with Sjöstrand to permit to understand partly this picture. Okay. Yes?
Excuse me, what was the meaning of the colors?
The corresponds, I think, to the density of states. So, yes, it's a picture. So you know that the density of state has the form m alpha plus the integrated density of state has the form m alpha plus n. And so you have different integer and you change of colors depending of this integer. It's okay?
I guess.
Yes, you are in gaps. And so in gaps, you can express the integrated density of state is constant for fixed alpha. But the dependence, when you move alpha, this expression has the form m alpha plus n. And so this is so the color corresponds to this. So this is a gap in the spectrum if you take alpha. So the pictures corresponding to gaps, and here it corresponds to constant integrated density of state. Okay, and then so of course I have not time to enter in the details, but why is semi-classical analysis involved? This is the only point that I want to say, is that so this idea was initiated by a physicist, Michael Wilkinson, which belongs to Berry's school. And the first point is to recognize that if we want to analyze the spectrum of the Harper operator, then you can look at the spectrum of a pseudo-differential operator with a semi-classical parameter. And then the first step would be to understand the spectrum modulo O of H infinity, and then start, after this first localization, we have to describe the first step of a renormalization procedure leading to two new semi-classical models. So this analysis is done through the analysis of the turning effect. So this is in the double well problem, we have a 2x2 matrix corresponding to the spectrum once it's localized. So in this case, in our case here, this 2x2 matrix is replaced by an infinite matrix working on L2 of Z2. And then you have to iterate things, so it's very complicated to manage all the details, but and in addition, it works if at each step you are in a suitable semi-classical situation. And so let's see. What is this pseudo-differential operator? So you can rewrite by looking at the union of the spectrum. You can see that it's the union over theta of the spectrum is the spectrum of this operator, where you have the we are on L2 of R, and tau H is the translation by H. So H is alpha or alpha over 2 pi. And so you have to do the semi-classical analysis of this model that you can also write in this way: cos H dx plus lambda cosine x. And so the first thing is to do this semi-classical analysis modulo O H infinity. And so this corresponds to start with the classical analysis. So you look to the curve, cosine, the energy level, cosine psi plus lambda cosine x. And then, the situation for lambda strictly less than 1 or lambda equal 1 is rather different. And the analysis we have done with Sjöstrand corresponds to this situation. So, and so we have to measure the turning effect between two. So the wells are now micro-local wells. And so this is the measure of the tunneling between two micro-local wells, which permits to realize, the first step in the renormalization procedure. So the interest of this approach is that it's not, we don't only treat the exact Harper model, so with cosine psi, with symbol cosine psi plus cosine x, but we are able to look at small perturbation in a suitable sense of this operator. And so our result can be applied to more general cases where the effective Hamiltonian in some region is close, is sufficiently close in a suitable sense to the Harper model. And so it's for the approach using the dynamics, so which were very powerful to solve the 10 Martini conjecture. We don't have this kind of result, I think. Okay, and so the result we have are semi-classical in the sense that if you expand the irrational alpha in continuous fraction, we have to assume that at least starting from some rank n, all the element A3 and so on, n and so on, are sufficiently large by some unknown large constant Cn. And then under this condition, the recursion argument works in the sense that when we do the localization, we can apply again the result of the first step to a new model. Okay, so of course you can think it was interesting at the time where you want to solve to have examples where the 10 Martini conjecture was true. So, but this only worked for this kind of alpha. So, but recently it appears that it's not. It could be interesting to use this more precise information about in this semi-classical construction to have other information about the spectrum. For example, do we have a positive Hausdorff dimensional spectrum in the critical Almos-Mathieu case? So, for example, recently I was asked by 3 Chinese colleagues to explain how we can use it, and so they need the details of the construction we have done with Sjöstrand. Okay, so time is going on. Yes, I have to go faster, so I will escape this. And then this was I don't remember the second one and the fifth one or something like that. The tuning, the analysis of the tuning was also done for Witten Laplacian. And so this was initiated by a very important paper by Witten, who introduced this special Laplacian, which has this form. H is a small parameter, and f is some function, some Morse function, at least at the beginning. And he was relating the spectral property of the Witten Laplacian with, for example, the Morse inequalities. And then there were more finer results giving other information related to the topology of the manifold. Okay, so here you have 2 objects. The first one is the distorted exterior differential, dfh. So you have a weight exponential f over h, and so we put h dx for convenience, and we look at the Laplacian, the associated Laplacian. So of course this can be done for p forms or p equals 0 to the dimension of the manifold. And typically, the Laplacian function has this form. And more explicitly is minus h square Laplace plus nabla f square minus h delta f. So we note that's so like in, you can do all what you were doing with the usual Laplacian and the differential with this Witten Laplacian. For example, you have this commutational relation. And here we are interested in the exponentially smaller eigenvalue of this Witten Laplacian on P form. So first on 0 form, but also on P form. So, and so they were in Witten's paper, there were this Morse inequality, which relates simply on the harmonic approximation of this operator. And there were other examples, another result, which was more related to the fine analysis of this distorted exterior differential. And this was in this second point that the tunneling analysis was important and was done with Johannes Sjöstrand. Okay, let's see, I have to go a little fast. So the basic idea at the beginning is that, again, by harmonic approximation, you can reduce all the analysis to a finite dimensional space. So looking at the space where you look to the eigenvalue, which are in some interval E of H, and defining the corresponding FL, you can have, also using the commutation between DFH and delta FH, you can reduce the Witten complex to a finite dimensional complex. And so here we are doing exactly the same that we were doing with the interaction matrix. We are just reducing the thing to a very low dimension problem. And then, so we get a complex with finite dimensional space, and the analysis of this complex, which is now finite, using the tunneling, measuring the exponentially small terms, permits, for example, in the paper with Sjöstrand, to recover a well-known complex introduced in topology. And so in the Witten paper, this was obtained by using a rather formal instantaneous method. So the rigorous proof by our approach it's much longer. It's based on all the semi-classical tool developed for the multiple well problem, and then there was our paper in 1983. Okay, then we were again interested to use this Witten Laplacian for 10 years later or 20 years later, about 20 years later, because there were a contribution about which was related to the Laplacian function, and considering either the problem in Rn or for the Dirichlet realization in some open set regard. And then the motivating paper was a paper by Bouvier, Koff, Gerhard, Klein, and later Bouvier, Gerhard, Klein, which proposed accurate asymptotic forms for the exponentially small eigenvalues. And then this was the motivation with Francis Nier, and at the beginning with Markus Klein, to try to come back to the techniques which were developed with Sjöstrand in the beginning. So at the beginning, we were thinking that it was simply an application of a direct application of the paper with Sjöstrand, but finally we need to redo a big part of the analysis. And so so this is the way we look in the Witten Laplacian spirit, but the probabilists look more to this version, so the Dirichlet form. And but we are not here, we are working in the usual L2 space, and here we are considering expression in the weighted space. But the two approaches are, of course, unitary equivalent. And then here was the kind of formula that you can obtain. So in this model, lambda 1 is 0 because exponential minus f over h is a solution corresponding to the eigenvalue 0. And then what is interesting is to continue the analysis with the k other eigenvalues. So if there are m naught minima, there are m naught minus 1 other small, exponentially small eigenvalues. And here are the kind of formula that you get. And in the approach by Bouvier, Gerard, Klein, the remainder has this form. So they got the important thing, that is the prefactor. Before, there was only information about the logarithm of this. So this was a very important improvement. And then with Francis Nier, we improve this by replacing this term by a complete asymptotics. Okay, so I think I have to go on. So again, there are many recent results in this spirit. So with completely different techniques, there are results by the Bismuth school, but in the semi-classical spirit, there are many recent contributions, changing the assumptions or looking at other cases that the initial cases. And I mentioned also that in the semi-classical analysis of the Fokker-Planck operator, the same techniques can be useful. Okay, so the last part, I have 5-10 minutes, or what do I have?
Yeah, well, it started a bit late, so
Yeah.
5 minutes plus. So
okay, 5 minutes. The last point is I wanted to mention, because it's a recent, quite recent result, was about the magnetic Schrödinger operator and superconductivity. And so we start from this model in some open set omega with a magnetic potential. So it's a pure magnetic Laplacian. And I assume that the magnetic field is constant. So this looks like a very simple operator, but this operator plays a very important role in superconductivity. And so we realize this first with Abderrahmane Moram, and then with Søren Fournet, that the spectral analysis of this operator plays an important role for the onset of superconductivity in the so-called type 2 superconductors. And so again, the question is to analyze the bottom of the spectrum. And there are two phenomena which appear. First is that the ground state is localized at the boundary. And the second point was that, and this was conjecture, there was a conjecture about this by Sternberg and co-author, the name I forget. And the second point is that the ground state should be localized near points of maximal curvature. And so this was the first goal, is to understand this. And then, because in the case where you have a symmetry, typically an ellipse, where you have 2 points of maximal curvature, the natural question, if you have the symmetry, is can we control the splitting? And so, the first part of the program consisting to estimate further eigenvalue modulo the main term, and 2 terms asymptotics, then infinite terms asymptotics was solved at the beginning by I participate to this. Then the question about the splitting remains open for a long time. So here is the picture. You see you have the ellipse, and you see a high concentration for the ground state near the 2 points of maximal curvature. Initially, I was aware of the first picture in this way was by a student of Uzi Smilansky, because in the beginning it was unclear this was true. Okay, so the question is to estimate the splitting. And then the first thing is first to have asymptotics. So in the case of a unique non-degenerate maximum. So progressively, we have the first term, and the second one, and so on. So the first term, theta naught, is related to the spectrum of this so-called de Gennes operator, which is a family, and we look for the infimum of xi of the bottom of the spectrum of this. And then here, the second term, you see that the curvature appear. And then if you want to understand the splitting in the one well case, you have to push at least one term more to see the labeling of the eigenvalue here. And so behind this, there is some operator living on the boundary, which is this one, theta naught h plus the second derivative at some specific value of xi, zeta naught h squared t squared minus c1 kappa of s, the curvature h3 half. So in the double well case, you see here that you can also look to a model, not exactly this one, because you have the question of to have the splitting for the periodic problem on the circle, a global one, not only localized near the one minima, but to take account to this. So all this leads to try to follow the program we have explained for the double well problem. So what progressively, so first, what I have presented as a result with Seurat and Fournet corresponds to the harmonic approximation or to the extended harmonic approximation. And then what do you have to do? You have to understand WKB construction. And this was performed by Bonnaillie-Hérau-Raymond about 3 or 4 years ago. And so we can get a kind of WKB solution. Then once you have this and the splitting formula, you get the candidate to be the splitting formula. And then the most difficult thing is to have the comparison between the WKB solution and the one-well eigenfunction. And this was this point which was solved quite recently. And so here is the theorem that you get about the splitting. You see that there is an oscillator exponentially small term, exponential minus s over h1 over 4. So this is this corresponds to something living inside the boundary. This is the turning effect is inside the boundary. Here you have an oscillatory term corresponding to the variation of the flux of the magnetic field, and then you have explicitly a computable term. And so this is in some sense the optimal result, and here is the numerics corresponding to the splitting. So you get some oscillation of the splitting as a function of the flux of the magnetic field. So H, so we are speaking about either semi-classical case, you put H before the derivation, or large magnetic behavior if you put the corresponding essentially to B equal 1 over H. Okay. So I have no time to give more detail. So to conclude, just mention 2 problems for which there are a lot to do. The turning effect in large dimension. So we have tried with Jöstrand to work on this, but we were always limited by a control of the dimension by the semi-classical parameter. So an inverse of the semi-classical parameter. So I think there is a lot to do. So there is a recent paper by Giacomo Di Gesù, which is in this direction. And the other point is tunneling between magnetic wells. So, just to mention that we don't understand very well, and this was also the difficulty in the previous statement, the tunneling, the Agmon estimate in the case with magnetic field. We understand very well when the case when you have an electric potential, but we don't understand when there are no electric potential, and that the leading potential is the magnetic potential. The analysis of tunneling, except rough Agmon estimate, is very open. Okay, so sorry to be a little too long.
Thank you for this very nice talk. So you can all thank very nice for this very nice talk. And the floor is open for questions. So you can raise your hand, post on the chat. Or we are not such a big group, so you can just unmute yourself and go ahead.
May I ask about the prehistory of tunneling? I mean, non-rigorous
Yes.
approaches. So, for instance, this formula about eigenvalue splitting obtained by the Stokes theorem. Who discovered that? And
so in the first, for the double well?
Yes.
For the double well, I repeat what I said. So to my knowledge, I think in 1D, you have this exercise in Landau-Lifshitz. So it comes back so it's rather old. I don't remember exactly the date. Then in 1D, you have the rigorous analysis by Harel. Between you have I think you have contribution by the Freeman, or where you have the formulas.
So
the formulas, I mean, but it's only 1D formula.
No, well, so I think I mean, my colleagues physicists have a different history.
Yes.
They, I mean, I think that Herring, Flicker. I mean, I don't remember, but there are some physicist papers.
I just speak about. I just mentioned mathematical contribution.
Yeah.
I'm not sure that, at least if you look at the books in physics, you never see the Agmon distance between wells. You can see maybe Feynman integrals where you at the end you can maybe recover something, but this idea that the turning is related to the Agmon distance between wells, I think is not present in the physics literature.
This is surprising, because this, I mean, and a non-rigorous version of this would be very natural. So
yes, but the people I think are always working with WKB approximation and things of this type.
But what about Bender-Wu?
Okay, for Bender-Wu, I don't remember exactly. What I know is that, so I know only Bender-Wu through the paper by Avron and Simon, which mentioned this conjecture by Bender-Wu, and then we prove it with Jöstrand. So this was related to the analysis of resonances. But in Bender-Wu, you have some radial properties. So in the radial case, you can again you can come back to 1D.
Okay.
But if you have not a particular situation of this type or separate variables and so on, I don't think this was present. I can, but actually, it's if you look to more recent books in physics, they continue to present in the old style. So
Yeah, this is yes, and this is unfortunate.
Yes, I think for this point it's unfortunate because this is the right way to understand.
Thank you.
Thank you. Any more questions?
Can I ask a question?
Yeah, please go ahead.
So hello, Benna, it's Søren. Thank you for a very nice talk. I wondered whether it's sort of easy to understand why the double well, the magnetic double well, is so much more complicated than the electric double well. Is there an intuitive explanation why we haven't been able to solve that?
The first question. So what has been done? So this was a part of the talk I have deleted. So what can be done is what corresponds to the harmonic approximation. So to find under suitable assumption that the minimum of B, say, is positive or non-degenerate, you can do the semi-classical analysis till modulo O of H infinity. And then you have two points. Can you do a WKB construction? And except very special examples, I think no result. And then the miracle which you have for the Schrödinger case with minus I squared delta plus V, it is that you have the Agmon estimate with this distance d of x, and that this d of x is also a solution in suitable region of the aconal equation. And at the moment, there are almost nothing in this direction. There was some paper with Harper-Sjöstrand in Pisa, where you look to the Schrödinger operator with magnetic field and electric potential, where the magnetic field is relatively small in comparison with the V of x. And in this case, already the decay for this kind of problem is not easy in the case with a magnetic field. We know that looking at the proofs, we know that the eigenfunction decay at least like in the case A equals 0. But it's only an upper bound. And we know also by examples, there are various examples, in particular by Laszlo Erdős, that the decay can be much stronger when you have a magnetic field. And so this decay through the Agmon distance corresponding to A equals 0 is not enough if you want to have, you will have upper bounds for the splitting, but for lower bound, it's not good. One of the other points is if you have the Schrödinger operator without magnetic field, you enter in the forbidden region by replacing psi by I psi. And so you have to work with the Hamiltonian V of x minus psi square. And you can do at least classical mechanics in this forbidden region. But now if you have a magnetic field, you cannot replace psi by I psi. Yeah, what you get is something complex. And so it's much more difficult to work with. And so at the moment, there are some non-optimal results, but I suppose that for the splitting, except if you have in some sense in a perturbative situation with respect to the magnetic field equal to 0, you have not so much. You have some result by Martinez or Nakamura about micro-local decay, to measure micro-local Agmon estimate and so on. But and this was one of the difficulty in the approach of Bonnaillie-Hérau-Raymond to have enough information for this. So it's I think it's very open.
Thank you.
Thank you. Thank you very much for the question. Yeah, anybody else?
Actually, I have another question, if I may.
Yeah, go ahead.
Can we go back to the ellipse? I'm a little bit, I should remember, I guess, but I forget what would the this splitting graph. I mean, you just the graph you had there. How would that look if somehow you only had connected the two wells through one part of the boundary? I mean, I think you have sort of a periodicity due to the flux.
Oh, yes, here, let's see, in this example, I hope I have reproduced the right state. So you have two cases because, so you can come back to at least formally the proof says that in order to understand the tunneling for this model in R2, it's enough to understand the 1D model. So this one is simplified, but essentially we can discuss with this one. And so we have this problem. So this is a kind of periodic problem. And there are two cases corresponding between one point and the other point by the other point. Are there two minimal geodesics from above, by above, or by or one of them? That is, there is a shorter square or not. And so, of course, the result will change. And so I think what we observe here is related to the fact that that you have the two things, the two. So the result I have written is correspond to the case where you have two minimal geodesics from above and from below.
Right. Thanks.
Okay. Any more questions or comments?
Well, what about tunneling on Riemannian manifolds, on curved?
A priori, there are no problem.
No problems. Okay.
A priori, so.
Is somebody working on this at the moment, or there is no?
I think the initial results are valid on manifold.
So there's no new complication expected from.
At the end, everything is localized in the computation near minimal geodesics between the two wells. So we have already a geometry behind this, which is related to the potential, and so the fact that you are on a compact manifold does not change so much.
Okay.
For Witten Laplacian, so you have this df. There are results where we replace df by a one form, and then effectively you can have differences depending if this about the property that omega is not necessarily a df, it's locally a df. But essentially the techniques are and the Agmon distance can be defined on a manifold. Instead of taking the dx square, you take the Riemannian metric and you multiply by the potential.
Okay. Thank you very much. Any other questions?
Of course, you can also ask about Lorentzian manifolds. I mean, about,
Oh, yes.
so
I don't know. Because no, I don't know. So all the no, I don't know. I was speaking about Riemannian manifold. Because all the, so you have to start from what is the Schrödinger operator, where is it, how is the spectrum and so on. It's much more complicated.
well, you just consider the Klein-Gordon operator, or and you can ask various questions about it.
Okay, I'm not aware of contributions in this spirit, but I don't know.
Yeah, that would be interesting, as yeah, if there is any technical difficulty related to that. So
well, there is a recent paper by Nakamura about that. So
okay, I don't know.
any other comments, questions? Well, if not, then we can thank the speaker again. So you can clap whichever way you want.